This is the final. Did everyone get this one?
Oh, actually, I get something different.
I'm sorry, what?
I got something different.
You got something different? What did you get? Let me draw this one over here. I don't have space. Let me see. So what did you draw? What did you get?
I got F at 3.
Got F at 3.
Which is number 4 inside. And
with number 4 here. Okay.
Yeah. And at 0, I have 6.
At 0, you have 6.
And my where is at 1.
Here is at 1. So this is Roya, right? Right?
Yes.
And this is Fabian?
Yeah.
Let me see. Okay. Anybody else who has something similar? Someone has something more? Something other than that? Everyone else getting either of these two answers?
I got the same answer as Fabian.
Okay. Okay. And the rest of the class, are you still working on it? Should we try to then work on it all together? First of all, now push 8. 8 will go where?
0.
At 0. And it will move R to 1, right? The push does that. It first puts the element at that location and then moves R1 to the right. Okay, then push 2. 2 is placed here, correct? And moves R to the 1 to the right. Now what will pop do? So
is
what
this
will
a stack, right?
I'm sorry, what?
Is this a stack, right?
This is a queue.
Oh, so it will take A off.
So is this Fabian? Did you assume we were working on a stack?
Yes.
Oh, this is a queue. And Roya, you thought it was a queue, right?
Yes.
Okay, so the pop will then move F to the right, right? Just F is equal to F plus 1. And this one is removed. So let me just erase this. So this is the result of so far here. Now when you push 1, we'll put 1 over here and move R here. Now when we pop, we'll move F over here and remove the 2. So we are here now. Now we call another pop and we will move F over here. Then a push 4 is going to happen here and moving R here. And then a push 6 is going to bring 6 over here and R here, which means that Roya's solution is correct. That's very good. And then Fabian thought that this was a stack. So that one is not correct. But now do you know why we got this?
Yes.
I have a question. When we remove number 1, why we move the front to the next one? I mean, because we just remove that, why the front doesn't stay there?
When we actually pop?
Yes.
When you pop something, why the front moves to the next one is what you're saying?
Yeah, I mean, when, yes. I mean, all the time it's like that. When we pop, we move it to the front, even though, I mean, the next one is empty.
So when you move it to the next one, it technically means that, so mostly you are thinking in terms of the real world lines. So these are some people who are standing in the queue, right? So when this person is removed, line technically moves like this, right? When this person is removed, the line technically starts moving like this. That's how the lines in the real life, the cues in the real life move. If you every time try to now move the elements one to the left, you are actually doing an expensive operation in an array where have to move the elements and all the elements one space ahead. Because A was gone over here, you move B in the place of A, C in the place of B, D in the place of C, and E in the place of D, which is actually an order n operation. And you have to do it every time the first person was being removed from the queue. Actually, in the real life, that's how people move in a queue. They keep walking as the other person leaves the queue. But to make it more efficient, instead of moving the elements, we will actually think about moving the counter itself. That is less expensive. We are just moving the counter, the index. That's less expensive than moving all the elements. So that was an order one operation. So what you're doing is, if these are a set of people who are standing in the line, and this is F initially, when we are popping A, instead of keeping the record that A was at the front, if we simply move the front to B, we indicate that now B is at the front by this F being here. Technically, then that indicates that A is out of the picture. So it's easier to move one variable every time, one counter variable every time. When B is gone, simply set the F to this one, indicating that they are gone from the queue. That's why the F just moves one to the right every time.
Thank you.
Because if we were to stay the F at,
my question was, like when the last one, like E, when we cross the E, when all of them A, B, C, D moves, the front will be on E, yes?
yes.
And then when we remove E, we don't have anything behind that. So why do we move the front to the next part, even though we don't have anything? Why that's...
You're asking only for that scenario, only for the last element?
Yes.
Okay. So if we want to do something different only for the last element, then we need to have a check if my front ever reached the last element. So we have to have an if statement where we are treating all the other elements in the same manner and the last one separately, to make a special case that move F only when you're somewhere anywhere else, but don't move F if you're at this position. It just is like a code that is supposed to work sort of equally for every instance. That really doesn't harm anything. It doesn't break the logic of the code, because when E was gone, if you now move F to an empty location, but so is R over there. So now if a new position had come in, something else had come in, it will just put F over here and move R to the next location, and front would automatically be pointing at the correct front. Instead, if you remain front over here and then you had something, then you would have to move front over there. So it just wants to maintain the consistency in the code. Otherwise, you would have to move front at that particular location when you were actually trying to add the first element, and then not move front every time. Because then you would have to check, okay, now I'm adding the second element, third element, then I'm not moving F every time on that. It just works. Yeah, it's just sort of like to maintain the consistency in the code.
Yeah, thank you.
Do we always assume that we're working with a queue when we use this data structure?
No, it's not assumed. It will actually say in the question. So when this sequence of commands is given, it will say either follow these commands on a queue or on a stack.
So the one that we showed was the array based, yes. But for
What is that?
the way that we showed this, it was the array based. And if we want to do the singly linked list, we should do with those arrows that points the pointers.
So this is a stack, this is an array-based implementation. If you do a singly linked list based implementation, you can just try to think of it like people standing in a queue. So when 8 comes in, you put 8 over here, then 2 comes in, then pop, simply remove 8, then push comes in, push 1, then pop again, then 4, and then 6. This is how the actual queue will look like, right? The real life queue. I can draw this again. I mean, for a singly linked list, just treat it as a real life queue. So when the push 8, so think of this person standing in a line 8, then another number comes in after that, 2. So 2 will stand here, then pop, the first one is to be removed, then push 1, 1 comes in line over here, then pop, the first one is removed, then pop, the first one is removed, everything is gone by this time. Then comes push 4 over here, then comes push 6. For a singly linked list, simply follow this logic, thinking of it like a real life scenario. Once you're done, you know that 4 and 6 now belong in the queue. So simply now, once you have this, you can simply draw them in a node, in each node, connect them with an arrow like this, and this should be null, and this should be head, and this should be tail.
Thank you.
That's the resulting answer. That's technically the same thing here, because this is your F and this is the last element. Only rear points to the next empty space, but this is front and this is the next element. That's what is represented over here. So everyone clear on that circular? Do you need any more examples on that one? I would suggest one thing: when you're going to take the exam, have if you do use Visual Studio, then you could have empty projects already created. So like create a console application, and then wherever you want to save it, you can have an SLL project. Ready here. And then the already created list, you can take this one from Titanium here. So for the singly linked list, you have an S-linked list example. You can copy that, put this one in the source file. And then you should also have the header files ready, where you should also have the zip file downloaded already in your folder, which I have over here. Then you can take the both HXX, the S-linked list, HPP and HXX here from here, put it in the SLL folder, and then attach it over here. So this one is, now you have, like, before you even begin, you can save this much time to actually have a project ready, and you can have this one open where you want to start writing the function. Do the same thing for another project with the DLL. So that given whatever question that you see, so for example, if you see this question here for the S-linked list, then it will say, define a function member in the S-linked list class. So you can straight away open this and start writing the function over there. So I would take this header from here, first of all, copy this one, and so anywhere where I would like to add the function, copy the header over here, and now try to fit this function into the class. So now, because I eventually want to run it, so I need to have this template line on top. Then I need to have, this is the return type, which is correct. This is the name of the function, but I need to have the name of the class before it. So you will have this one here, and then, so basically you have created the skeleton of the function that you're going to write over here. And if you want to write the recursive version, then you need to have another function, which is the private function. So simply copy this skeleton and paste here. Simply call this one a helper. So this is how you should actually start writing functions, because eventually you want to run it and see if the function is working. Now you see these red lines indicating the error. That means that we have to have the headers in the HPP. So this is something that you should actually just start with, and then you can actually start filling in the code into this into the skeletons that you have just created. You can just start writing the code over here to answer the question. One thing, when you want to write a recursive function, you should try to actually envision behind the scenes, basically a stack is being implemented for the recursive calls. So for example, always in the public function, you should be, the public functions are very similar across every question. So no matter whatever function you're going to get, you're doing the same task in the public function. The solution is already available to you. What you have to write in the public function. Every time you basically just write node star PTR, set it to head, and head's next in a doubly linked list. And then you simply call the helper function. And the helper function with the pointer and what you're receiving over here. So So if you're calling with, so of course, whatever we are receiving over here, that we need to pass in the helper function, but now we are also sending the head as pointer over here. So that one has to be received over here. So you need to have the node star PTR here as well. So we need to update this argument in the private helper function over here. So mostly, I mean, across any function, the public function for the recursive is going to look very, very similar. For all singly linked lists, you know, you can see it's very similar for doubly, you just have the heads next, but you have to see what you're calling the helper function with. Have the additional element also going in there, but if you don't have the additional element, then you just call it with the pointer. And when you want to approach writing any recursive function, the approach is always to think with the base case. So before even thinking of the recursion, always think that you're ending it. So think of ending the recursion before even starting it. So the best way is always to write the base case or the ending case first. And what is the base case? The base case is the simplest case. That means that the list doesn't even exist. So that means that the pointer is equal to null pointer. That means the list is non-existent. Then what are you going to return as the frequency of the element? If the list doesn't exist, the frequency of anything is 0. Else, then everything else goes over here. So now you can see while you are actually writing that function, you're now narrowing down your task into various bits and pieces. And eventually the whole point boils down to this portion over here where you have to write the logic of the finding frequency. And the logic basically means is it's how you are actually, you know, thinking of in terms of even not writing the code. When you have a list like this, then if you're looking for how many times 2 is in the list, then what you will do, you will keep on comparing each node's data with the whatever you're looking for. So the equivalent of that is going to be, okay, so currently I'm on whichever node is that pointer's data equal to the element I'm looking for. Then, okay, I have to count the occurrence of that element. So for example, if 2 was over here, so I have to count the occurrence of this element 1 plus and go on looking for the rest of the list like I looked at the very beginning. So I'll keep repeating this and just call the freq helper again with this one, with pointers next. But if the data is not found, then I'm not counting the occurrence at that node that I am because the data is not found. So I don't count that node. I simply go on to look for the rest of the list. So I don't do a 1 plus at that time. So that's how basically I would approach writing a recursive version, starting from the public and down to the helper. And if you want to check, of course, the best way to check is like you have the ability to actually check it, run it, and see if the function is working right. And you can call that function in the CPP file. But then there's another, I mean, if you want to see what really happens in the recursion, is like there's a stack actually that is created in the memory that will be called with, first of all, the pointer is over here, the PTR is over here. So that would be called with 2 over here. That one then says, and you're looking for 2. So it will say, is the pointer's data equal to element? Yes, in this case, yes. So you will do 1 plus, And then you will call with the next one that calls with 6. Then the 6 calls is over here. Then you call with 6 and then you do, is the data at this particular pointer equal to 2? No. So then you are here. So you'll simply call with the next one, which is 2. This is exactly how the entries get pushed on with the stack behind the scenes. Then the 2 is called, then you say, yes, it is actually equal. So then you'll do 1 plus the next one. Yes, Fabian?
I put on the chat the question.
You can say it, I cannot see the chat.
Oh, so what if I did the condition like in a different way where I have count defined and inside the definition of count, I check for the element and I return 1 or 0, and then I just use the count in the return. It's just a different way to write in the if statement.
There. So you're declaring a count every time? You're declaring an integer variable every time in the recursive call? Is that what you're saying?
Yes.
Well, when you do something like an int, or maybe you're doing an int c over here.
It's not an int, it's a size t.
Yeah, size t, yeah. So that means you're creating a new variable inside each recursive call. What happens is, it's a practice to do as that as well. One thing that I want to do is, as long as you can, avoid using local variables between successive function calls. One, it's saving space, because as it is, this is what is happening without having any local variable. But then if you every time set the c equals to 0, in the next successive call, actually a new, some people tend to make mistakes on using those local variables. So sometimes every time when you're actually doing a new int c is equal to 0, actually, even though if you're counting 1 plus c every time, that doesn't make any change, because every time you're also in the successive call setting it back to 0. That's not a good practice at all. If we are using local variables, we need to understand how to use them correctly, or else avoid using them. So the mistakes can be made if we use local variables, because sometimes for the successive recursive call, the new int that you have been created, okay, that particular int is local to that recursive call, and that particular variable will be doing what it is doing, and then return whatever value is supposed to be returning correctly. But depending on where you are declaring it, it can actually always be setting it to 0 every time. So I would have to see that how it has been used, and then I'll see, okay, if it has been used correctly or not. But you will see in my solutions, I always tend to avoid using local variables as much as I can until I cannot anymore, until I'm forced to use local variables. Does that make sense?
Yes, thank you.
So I was here then. At 2, you did a 1 plus then the 1. Finally, for the 1, you're calling, because it's not found at 1, you're calling the null pointer. And then finally, for the null is where you start returning. This is how the function actually, the calls actually return. And the stack has to be emptied after, then only the recursion ends. So when the pointer is null, you actually return 0 from here. This one will be popped and return 0. This one function call, it returns back. It returns 0 over here. This is popped. And then this once call is complete, it returns 0 over here. This call is pending. You have to do a 1 plus 0, then this call is complete. And because this 1 plus 0 is 1, you return 1 over here. And then 6 was waiting on 2's call, and then it returns 1 where it was called here. And finally, this last 2, that was actually the first 2 over here, this one is waiting. This one is the last item in the stack. And now you have 1 plus 1, that is 2. This call is complete. The stack is finally empty, and it results in 2. So this is exactly how recursion works. It calls from the first element but goes till the last element, then keeps returning the last in first out way in reverse order. It actually returns the answers and gets out when the actual first element is done. So if you would like to bring any more questions from any of the coding question that you might think, you can just look at, if you want to get some practice, just look at some sample programs online, anything that is on the same difficulty level as these questions, and try to solve them yourself instead of looking at the solution. And if you need help, you can bring those questions in class on Tuesday. We'll again do the review on Tuesday. And then on Thursday, you should take your exam. So just as a reminder, the class on Thursday will still be on, in the sense I'll be here, but you can choose to take the test anytime. In case you want to take the test during the class time, then you should actually join the Zoom session for the class on Thursday. All right.
If you want to get like coding examples to work on, how can we get that? Is it possible for you to give us some example to work on?
For coding examples to work on, you can actually, one thing I recommend, always try to visit the SI sessions. They have very good coding examples for you. Yes, they actually have. Derek, yes?
Oh, yeah. Yes, Professor.
Yeah, they have very good, SI sessions have very good practice exams actually for you. So you should go to the SI sessions, and they have some very, very good other questions as well, the multiple choice and coding questions. And students actually like working on them. I've seen that in the past. So one thing you should do is that. And other thing that you can actually do is on the internet, you just type, okay, recursive problems. Recursive practice problems with solutions, but don't look at the solutions. Just solve them yourself. So you have a lot of them. See, so many problems you have. Palindrome is something, it's actually, check if a number is palindrome. You know what a palindrome is? So some interesting strings that are palindromes. So, okay, let's see. Some words that are palindromes. Civic. Civic is a palindrome. Radar, level. It means that if you go from left to right on the word or right to left on the word, then that spells the same. So spell civic backwards. it's spelled the same as it is spelled forwards. Level, same. Race car also same. Madam, refer. So these are, and then if the problem is, if an input is given, so maybe a string is given, not a number, or number could also be a palindrome. So for example, 313, reverse is also the same. 3132, and then 313 is also a palindrome. So given a number or given a string like civic or something, if that is an input, you have to write a recursive function to check whether it's a palindrome. And you can fit that function in a singly linked class if the singly linked class is actually carrying all characters instead of integers. So what if my SLL over here has characters instead of integers? I could just make it a CHAR. And I would just add, say, C. So if I have built a list like this, then I can first run to see, okay, my list actually has those. What is the error? Oh, okay. So this is my list. So currently, this is the list that is built already. But now, is this the word that you have in your singly linked list? Is that a palindrome? So you have to write a function is palindrome in the class SLL to check whether it's a palindrome. So return 1 if it is, return 0 if it is not. And you have a lot more problems that you can get from here. Many, many more problems. And this is just one place. You will have so many places. And they are actually also giving you solutions, which I would recommend not going to before actually trying them yourself. But this is just geeks for geeks. But then you have, again, Stanford. I mean, you will go to a lot of these university websites. You have warm-ups. Look, I see so many. There's actually, and these are very interesting. Even for when you will study for your interviews, you should try them on your own. Who knows? They will be asking you 1 or 2 of these in the interview. Right?
Thank you.
And then if you're not, I would recommend not looking at the solutions, just keep working yourself. And then bring any question that you're not able to solve, then bring them to class next time. Okay, so all right, then let's wrap up. And just remember to do the homework, and let's meet again on Tuesday, okay? All right, then. Bye, everyone.
Thank you. Bye.
Bye.